Welcome to the third and final part of Snowball physics. Using the skills that you've hopefully developed from the first two parts, this part will be a little bit more interactive. Will be a little bit more expected for you to do. So let's have a look at the type of scenario in part 3 here. Well, this time if we combine the previous two scenarios, we've got a projectile being launched from a height, and it's also being launched at an angle, so you can see that's a mixture of the first two scenarios. Now this particular projectile, or snowball, is being launched at 40 meters per second at an angle of 20 degrees from the horizontal. So what I'm going to ask you to do first is just to fill in the information that you know in the SUVAC grids. Okay, so hopefully you've had to think about what information we know we can fill in the grids there. Well, we're ignoring air resistance once again, so the vertical acceleration is going to be minus 9.81 and the horizontal acceleration is going to be 0. And so hopefully the first thing that you've recognised it's necessary to do is to take that velocity and break it down into a horizontal and a vertical component. So we'll do that down here. So if we draw a vector diagram, our initial velocity is 40 meters per second, and that can be broken down into two components, a horizontal component and a vertical component. So we've got a right angle triangle, and so the horizontal component is going to be 40 cos 20, making sure your calculator is in degrees mode there. 40 cos times cos 20 gives us 37.6 meters per second, and similarly the vertical component will be 40 sine 20, which gives us a vertical component of velocity 13.7 meters per second. So returning to our grids there, the initial vertical velocity is plus, since it's in the upwards direction, 13.7, and the initial horizontal velocity plus, since it's to the right, 37.6 here. And once again, with no horizontal acceleration, the horizontal velocity will remain constant, plus 37.6. So hopefully you've set the grids up in the way that we can see there. So what questions might you be asked in this kind of scenario? Well, it's similar questions to those that we've looked at before. You may be asked to calculate the maximum height of the snowball, of our projectile. You may be asked to calculate the time it takes to reach its maximum height, or you may be asked to calculate the total flight time, the time it takes to hit the bottom down here. Let's just add some extra information here. Let's imagine our snowball is initially at a height of 30 meters from the ground down here. You could also be asked to calculate the vertical velocity on impact, or just before the snowball hits the ground, and you may be asked to calculate the angle at which it hits the ground, or the overall velocity as it hits the ground. Well, let's just take one or two of those questions and have a look at how we can approach it. It's using the similar techniques as we've seen before. So let's calculate the flight time. So I'm going to ask you to do that. Can you calculate the total flight time for the snowball to just before it hits the ground down here? Okay, well, hopefully you've had time to think that through. The first question you have to ask yourself is what to fill in the grid. Now if our snowball is just about to hit the ground, it will have travelled down relative to that start point 30 metres down. So the vertical displacement just before the snowball impacts with the ground will be minus 30. And the initial question was, what's the flight time for the snowball just before it hits the ground down here? So we've got three values in our grid and we need to calculate t, and we've got s, u and a, and we need to calculate t. So let's just have a think about how we're going to do that. Now if we look at our Subat equations here, let's just a quick reminder again before we look at the Subat equations. We're trying to find t and we have s, u and a. Now the first equation does involve s, u, a and t. If you've tried to use that equation, you may have found that there's an issue because u isn't 0 and s isn't 0 either. So in order to find t from this equation, we have to solve a quadratic equation, and that's a little bit difficult to do. So rather than find the flight time first, a slightly easier way into this question would be to find v, the final vertical velocity just before the snowball hits the ground. That's a little bit easier to find, and then once we have v, we can get t just a little bit more easily. So let's have a look at that. So if we start down here and let's calculate the final velocity, the final vertical velocity of the snowball just before it hits the ground. Well, we need an equation that links in s, u, v and a. So v squared equals u squared plus 2as. If I just move that there to create a little bit more space, and we're trying to calculate v. So let's substitute in what values we have there. V squared equals 13.7 squared plus 2 times minus 9.81 times minus 30. Just bring that onto the page there. Remember, with an equation it's always best just to indicate whether you're applying it to the vertical or the horizontal. All the information in here should be applied to the vertical. If I just switch to switch from the red pen to black pen, I think you'll find that's just a little bit easier to see on the camera here. So if we just calculate v squared, we've got 13.7 squared plus 2 times minus 9.81 times minus 30, and that gives us 776. V squared equals 776.29, and so v, if we take the square root there, will be 27.9 meters per second. And again, it's going to be a downwards vertical velocity, so we need to think about whether that's a positive or negative number, and it'll be minus 27.9. So if we turn to the grid there, that will give us minus 27.9. And if we calculate the final vertical velocity, that just makes it that little bit easier to get that flight time there. So if we move down now to calculate the flight time, and remember, trying to calculate t, and we have s, u, a and v, so we have our choice of equations. If we use v equals u plus at, this is being applied vertically, and if we rearrange that algebraically, t is v minus u over a. If we substitute our values in, remember we calculated v just now, minus 27.9, so minus 27.9 minus u. U we obtained here, and we filled in the grid, 13.7, the initial vertical velocity, 13.7, and we divide by minus 9.81, and that gives us, if I just work that out on the calculator here, minus 27.9 minus 13.7 divided by minus 9.81 gives us 4.2 seconds, and so we've been able to calculate the flight time. Now remember, we said if to calculate the flight time we found it easier to calculate v first, and that allowed us to calculate t relatively easily. If we hadn't calculated v first, if we just cover that over there, if we had s, u and a and we were trying to calculate t, remember, going back to the Suvat equations, if we don't know v, we'd only be able to use this top equation here, and if s and u is not 0, it becomes difficult to solve that equation as it's a quadratic. It can be done, it's just some students aren't fully familiar with solving quadratic equations. So one final question then for this type of scenario, and if you pause the video it'll give you the opportunity to try it for yourself. What's the overall velocity of the snowball just before landing, and at what angle is the snowball travelling just before landing? Well, if you remember, it involves using the head to tail method. So we've already worked out the final vertical velocity of the snowball just before landing, minus 27.9. So we have a vertical velocity of 27.9 meters per second, just before the snowball lands, and we have a horizontal velocity which remains constant of 37.6 to the right. So using the head to tail method, it doesn't matter which way around you do it. We could have shown the horizontal one first and then added the vertical on. Here we've done the vertical one first using the head to tail method, then add the horizontal on. Either way you're going to get the same resultant velocity from here to here, and if we use Pythagoras' theorem, that will give us this v here, the overall velocity. So if we just take 37.6 and we square it, and we add 27.9 squared, and then we square root the total there, using Pythagoras' theorem, that will give us v 46.8 meters per second. And if we actually compare that with the initial overall velocity of 40 meters per second, we can see that the speed of the snowball has increased as it's fallen this height of 30 meters. And if we work out the angle from the horizontal, if we're working out the direction of this from the horizontal, it would be this angle we need. And remember, if you ever find a Z shape, then the angles inside the two parts of the Z are going to be the same. So this angle, the angle of the projectile below the horizontal, is the same as this angle, theta here. So if we work out theta, it's going to be the inverse tan of 27.9 divided by 37.6, and we just calculate that to give us our final result there. Don't forget to put your calculator in degrees mode if you had it from radians mode, and that gives us 36.6 degrees is the final angle of our snowball, angle below the horizontal.